So for the last video of this week, I decided to do the optional section on the end of Chapter 4 rather than to start Chapter 5. And the reason is the content that's in this section of Chapter 4 we'll see again in about 2 chapters, and it's often confusing for students, so I thought if we introduced it now, it might make Chapter 6 go a little bit smoother. And what this is really about, so kind of picture that you're out on the road and you see a road sign, like a stop sign, for example, and you ask yourself, how were the decisions about the support structure for that stop sign made? How did they decide how wide of bolts to use? How did they decide how deep to dig the pole in the ground and things of this nature? And whenever you're thinking about support structures, it really comes down to a question of static analysis. And even though we're not too far into static analysis, we know that that boils down to understanding the loads that whatever the body is subjected to. So in the case of a stop sign, of course, it has mass, so it has a weight, and the support system will have to counterbalance that weight. In addition, there might be rare occasions that someone like strikes the stop sign, maybe with a bat trying to do vandalism, or maybe with a hand, something like that. In that case, it would be actually a point force, the kind of forces that we've looked at up until now, where they're by and large kind of located at a single point of application. However, the majority of the loading that will occur on that stop sign is going to be the wind actually blowing on the stop sign. And when you think about quantifying the type of load that the wind will present to the stop sign, that's going to be a force that's distributed across its entire area. And as you probably remember back from your physics course, whenever you have a force that's distributed across an area, you actually refer to that as a pressure. So that's what the book is using here for terminology. They're saying the wind pressure acting on the sign is distributed as shown, and it looks to be uniform. And the idea is if we look at this distribution, first note that the units of these little force vectors are in units of PA, and that's the abbreviation for Pascal, which is the SI unit for pressure. So if I were to talk about how much force is being exerted at a particular point, remember that when you have any kind of density, including pressure, if you evaluate, assume that the density is expressed by a function, as we'll see in the next slide. If you want to determine how much force is acting at a particular point, you can't just evaluate the density function at that point. You actually have to use the concept of calculus of integration. You have to basically sum the density over some very small area near the point of interest, and that's what allows you to determine how much force is being exerted at that particular point. Of course, if we wanted to determine the total or aggregate load that's acting upon that sign, we would need to sum up all of that density, and that's a process of just performing a definite integral over the bounds of the actual sign. So what would be the purpose of doing that? Well, remember up until now, we talked a lot about equivalent force coupled systems. And very often I've kind of motivated those type of problems by saying, well, if we could come up with an equivalent force coupled system at the point where we actually want to install the support structure, we would know how strong, for lack of a better term, our support structure has to be. We would know how much force it has to overcome, and we would know how much torque that it has to be able to maintain. Remember that torque and a moment are kind of the same idea, just different words for the same thing. So if we want to design the support structure for a sign like this, and it's acted upon by a distributed force, we're going to need a way to replace the distributed force with just a single force acting at a point. And that's what this section is about, and we're going to look at it in a lot more detail next time. So the type of things that we want to be familiar with seeing, we're going to start the problems, is probably not too surprising to you, to make the math easy in one dimension. So say we have some sort of beam structure, and say it's subjected to a continuous load whose density actually varies across the span of the beam. So this is often called the loading curve. And notice that it's expressed as W as a function of X, meaning that if I plug in a particular X value, I can find out how dense the loading density is at that particular point. However, if I want to actually determine the force around a particular point, as I mentioned on the previous slide, we're going to need to actually multiply the density times whatever the kind of length, or I guess I would say, dimension information that the density is expressed in. So you can have force expressed in things like newtons per cubic meter. It's like a force density over a volume. More common, you have a force density expressed over an area, newtons per meter squared. But here, since this is only a problem in one dimensions, this is going to be a newtons per meter force density. So the way that I'm going to actually determine how much force is acting on a particular little area is I'm going to take and I'm going to chunk up my axis of the beam into some little infinitesimally thin chunk. And I'm going to denote that, as I typically do in calculus, by dx. Now, what would happen if I actually multiplied dx, which is going to be a width, times the actual height of that function? Well, first of all, what you might want to tell me is there's not a unique definition for the height of the function, because over that little interval dx, the function is actually varying. However, the idea is if I let that little interval become infinitesimally small, that for all practical purposes, on both sides of that area, the actual value of the function will be the same. So if I then take the product of dx times wx, if you notice, that's giving me the area under the loading curve. And what that actually is the force that's acting upon that infinitesimally thin part of the beam. So since it's an infinitesimal amount of force, we will call it dF. So remember, in calculus, d just denotes an infinitesimal quantity. So how would I actually determine the entire force acting upon that beam? Well, all that I would need to do is repeat that process across the entire beam. I would need to sum all of these little dFs. And that's exactly what we're doing here by calculus. I'm integrating over the entire length of the beam, which allows me to sum these infinitesimal forces. Substituting in each little infinitesimal force is just the value of the density function times dx. And what is this actual quantity here? Well, remember, if I integrate a function over some fixed domain from 0 to L in this case, and that definite integral, that's going to be a definite integral, is just going to be the area under this curve. So that's what your text actually means by A. If I compute the area under the loading curve, that will tell me the net force that's actually exerted on the beam, or the total force. So that is giving you the magnitude of this resultant force. The problem is, say just the area under the curve turned out to be, 40 newtons. What you're doing is you're replacing the distribution of the force by an equivalent magnitude. But in order to really model it as a single force, you have to know where to put it. So here, they've kind of shown it, well, what if you just put it at this distance x bar? And for those of you that have seen physics beforehand, you're probably familiar with the fact that the reason you put a bar over the x is it kind of gets to the idea of the centroid, or some kind of geometric moment of this area. But basically what we're going to do is we're going to choose in the next slide where to place this force. And since it's a one-dimensional problem, all that I basically have to choose is how far I need to put it away from the origin. So going back to our kind of viewpoint of forces, it's causing translation and causing rotation. Here, when we actually find the aggregate or the resultant force by integration, what we found is the component of this load that's actually going to induce translation. This single force tells us how much that loading curve is going to tend to push the beam down. However, it doesn't give us any information about how it will tend to induce rotation in the beam. Or when we actually get into internal forces of the beam, it doesn't give information about what's all going on inside the beam. I don't want to go too much into that because this video will get too long. So the way that we're going to choose where to put this equivalent force is to make sure that the tendency of the single force to induce rotation of the beam is the same as the tendency of the distributed force. And that's all that this is saying here. If you think about this integral that they're doing, if I were to compute the moment of each of these little infinitesimal forces, dF, about the origin in this case, first thing you'll notice is if you just pin the beam at point O and you push down, you're going to induce a clockwise rotation. So that's why the book is all of a sudden adopting a clockwise rotation as positive. Remember, it's just as long as you're consistent, it doesn't matter what your sign convention is. So this will just make things a little bit easier. So if I think about how much this force induces a moment about point O, what will that be? Well, the magnitude of the force is dF. And remember, the scalar approach to moments, you need the magnitude of the force, you need the direction, which we already determined, and you need the perpendicular distance. Well, how far away is this infinitesimal force dF from the origin? Well, that's just our variable x. So this term x dF, if you just focus on that inside the argument of the integral, what that is telling you is how much this infinitesimal force is going to induce rotation about the origin. So if you integrate that across the entire beam, what you're finding is the total tendency of this load distribution to induce rotation about point O. So that's all that's going on here. So this x is nothing more than the perpendicular distance. This w of x dx, if you remember, is just df. It's nothing more than the area of this rectangle. It's dx wide, and it's w of x high. So if you think about what we have here, we have an expression for the total rotation that the distributed load will cause about point O. However, what we're interested in is making sure that that's the same as the setup that we have for our equivalent single force. So the book kind of makes this a little bit actually complicated here. This integral of L wx dx, if you think about it, that's just them trying to look smart and talking about the entire area under this curve. So remember that the entire area under the curve is the magnitude of the force. So when you take the magnitude of the force and you multiply by x bar, that's just a very simple calculation of the moment of the resultant force about the origin. So what we're going to say is that Fr times x bar, and remember Fr we're going to call A, has to be equal to this crazy integral expression that we have up here. And that's exactly what the book did. If you multiply this back out to the other side, x bar times this integral is nothing more than the rotation about the origin for the single force system. And this integral that we have on the top is nothing more than the rotation about the origin for this distributed force system. And we're just saying those two things have to be equal. But the beautiful thing is this is going to give us a formula to determine where we actually need to apply our single equivalent force. If we have a distribution of force density, or we have a loading curve, the same word for the same thing, as long as we can integrate that And as long as we can integrate the product of x times that, we're going to be able to compute what this is. And what we'll see is that this is actually called the first moment of this actual area about the particular origin or the axis. There's different ways to talk about it, and we will talk about it. However, a term that you want to start to hear and think about is this idea of a centroid. So basically what is happening here is if you have a density function that defines an area, and that is actually a loading curve acting upon your beam, the point at which the equivalent force acts is at the centroid of that area that is defined by the loading curve. So it's a little bit confusing because when you think about centroids, you think of centroids of area. We're going to talk about center of gravity and where you would actually balance an object if it was of uniform density by your hand. So just remember, this isn't really an area here. It's an area that's formed by a function on the top, and that function is actually defining the loading density. So let's look at a couple different examples. Your book tells you that basically they're not going to bother you with integrating yet. We're going to talk about integrating power law functions when we get to that appropriate point in the text. However, for now, we're just going to rely on the fact that the definite integral of simple shapes is just the area under the curve. So we know how to compute the area under the curve for a rectangle, and we know how to compute it for a triangle. And for the actual first moments that you need, those integrals of x times dA, there's going to be things that we can actually look up. And it's probably not going to be surprising to you that when you have like a uniform distribution that's going to form a rectangular area, that its centroid is going to be right in the middle. So if you notice when they've replaced this distributive force by a single resultant force, how did they pick the magnitude? Well, technically they integrated this distribution over the entire length of the beam. But since it's just a rectangle, we can determine what that area is as just the height times the width. If it's 400 pounds per foot in height and it's 10 feet wide, if we multiply those things together, we just get 4,000 pounds. So this quantity is nothing more than the definite integral of this distribution, which is just the area under the curve, which for a rectangle is just the width times the height. Where are we actually going to put it? Well, we're going to put it at the centroid. And for now, this is just something that we're going to look up. And if you look it up, what you will find is that it's nothing more than half of the actual, for a uniform distribution like this or a rectangle, the centroid is just half of the width. So that's why they're placing this at 5 feet. For the case of the triangle, remember that the area is 1/2 the base times the height. So if the height is 600 newtons per meter, if the base is 6, if you multiply those two things together and take 1/2, just take half of 6 to make it easy, that'll be 3. 3 times 600 newtons per meter is 1,800 newtons. And where do you actually place that? Well, if you look this up from the text in the back of your text, well, you don't have a back. It's on the tables that are in your electronic text. And I can post those on Canvas if it helps. What you'll find is that it's 2/3 of the way over from kind of where the triangle starts. So what I mean by that is the triangle tapers from here up to a maximum height. So if you go 2/3 of the actual base, which is 6, you'll notice that is 4. 2/3 of 6 is 4. That's where the centroid is actually located. And probably not surprising to you that it's going to be closer to the right than to the left because there's going to be more area under the curve towards the right portion of the beam. So that's all that is actually going on here. That is just describing that all of this is basically the calculations that we described on the last page. So hopefully the motivation for why we need to describe distributed forces just using a single equivalent force is clear to you. And hopefully you get that the way you do it is you determine the magnitude of that equivalent single force by integrating the load density function across the entire beam for the case of a beam. And you determine where the actual point of application is by finding the centroid of the area that's actually formed by the shape of the load density function. And if you're just watching me do it, I'm guessing for now you're watching me talk about it on slides. A lot of this won't make sense. However, we'll actually start next week with an example, and we will have a homework problem like this on the actual homework for next week, along with some of the other stuff in Chapter 4 that we didn't cover yet. I think if I remember correctly, I'm not looking at it now, but our Chapter 4 homework, we really only got up to the point of computing moments using the scalar formulation and the vector formulation about a point. So we need to do some stuff of computing moments about axes. We need to talk about doing couple analysis, equivalent force couple systems, really puts all this together. Just a bit of a spoiler alert, when you get this question on the test, it's definitely going to be an equivalent force couple system because that really asks all the key components of everything that we've covered in Chapter 4 so far. And in addition, we need to do some of the replacing force distributions by a single equivalent force. So hope everything is going well. I know I'm behind on getting you that information about the grades and extra credit, but that's on me. So that'll just extend your ability to complete the extra credit. Don't sweat about it. know that your grades are likely going to be higher than what is posted within Mastering Engineering, and that you will get both extra credit for your work that you turned in the Dropbox, and if you're committed to doing the work to make sure that you understand the material, I'd be happy to give you an extra credit opportunity. So thanks, and I'll talk to you all soon.